All right, so class, we're definitely, yeah, you can get one of those lights, not both of them.
I can.
How's that? Is that better? All right. Oh, but then you can't see me when I do all my great stuff.
Oh, they still could see you.
Oh,
no.
I know, just out on everything. Okay, that's fine.
It's 11:30 in the morning.
Win some, you lose some. So we're talking about gravitational torque and the center of gravity. Can anybody tell me from your readings what center of gravity, or maybe just from your common knowledge, what's center of gravity all about? Oh, we got Hensley first here. Yes?
Point nearest something on the object. I don't know.
The point nearest something on an object. Partial credit, kind of, sort of. Anton, I see that hand. Thank you for having your hand up.
The point where the weight appears to act.
The point where the weight appears to act. You remember how I said we are going to objectify objects in this class?
Great.
It's never a good idea to objectify people unless it's for the purposes of physics, okay? But we are going to reduce everything to what? We have a whole complicated system, like a car. What are we going to reduce that whole car to? A dot, okay? And when we were dealing with motion, we said, okay, imagine that dot was just, moving along back and forth. It's really good for when you're a poor artist like myself, okay? But when something is rotating as well, we can also, we don't necessarily want to reduce it just to a dot, but we can act like that entire object is located in one spot, okay? And that spot, that location, if we're talking about a three-dimensional object, it would have not only an x and a y coordinate, but also a z coordinate, okay? But we can act as if this entire object is located at just one point in space, and all of its mass has been shrunk down, black hole, condensed into that one singularity. So if this weighs, about 7 newtons, right now it's 7 newtons and it's taking up this much volume, but we can, for the purposes of doing some equations and things, we can imagine that all of those 7 newtons were condensed into an infinitesimally small point in space. Does that make sense? And that point is called the center of gravity. That is where we can act like all of the weight is look at all the mass, okay? And what happens is then, let me just give you an example of the problem here, okay? This is a far better item to talk about, okay? What is this meter stick made up of? Here, we definitely need the lights. What is this meter stick made up of?
A stick.
Not made up of meters. Made up of wood. Particles, okay? So at the smallest level, you've got atoms. You also have groups of atoms, and you've got your smaller subatomic particles and stuff like that. But if we were to figure out, okay, what's going on with this thing, all right, well, each one of those atoms have mass. The proton has mass. The electron has mass. Not a lot. The neutron has mass. And each one of those protons, electrons, and neutrons, or each one of those atoms, if you group them all together, is sitting there. And it's just a little bit above the Earth. And so the Earth and that just one of those little atoms are going to be exerting a gravitational force of attraction on each other. The Earth is going to be pulling down on the smallest little atom there, and this is going to be pulling up on the Earth. Although when I let it go, that atom is going to then accelerate towards the Earth very quickly. The Earth will accelerate towards it, but not as quickly since it's a really heavy mass. Okay, so if I want to figure out, since this atom is not only just in free fall, it would be actually connected to the one next to it, and this one to the next to it. If you remember from chemistry, there's different ways that atoms can be connected to each other. You've got your covalent bonds and your ionic bonds, and we're not going to really get into any of that stuff. But the point is that, I would say, well, this atom right here on the very end, it has this mass and it's being pulled down. And the one right next to it has this mass and it's being pulled down. And then the one right next to it, okay? You see where I'm going? All of those are being pulled down, and there are trillions upon trillions, more than trillions, okay? Like we're talking in the 30, 40, 50, 60 zeros after, in terms of the number of atoms that there are here, okay? And they're all being pulled down. Even with really awesome computers, it's difficult to do a physics calculation with all of that, right? To actually figure out what would happen to this. Well, here's the advantage of physics. We're going to reduce all of those atoms, all of those molecules, to just one single point. And we're going to add up all of their masses, okay? And reduce it also to just one of this point. And we can say, all right, well, actually what's going to happen to this meter stick is gravity is going to pull on it as if all of the weight was centered at that one location, at that one point, okay? That's where we can consider gravity just being exerted on. So what I can do is I can say I don't have to actually figure out what's the gravitational pull on this one and on this one and on this one and on this one and on this one. I actually can just say what's the gravitational pull on a point right here that weighs 2 newtons. Does that make sense? So that way I don't have to worry about all of those different things. Now, the center of gravity has some interesting properties about it. One of the interesting properties about the center of gravity is that if I can locate the center of gravity, okay, and I can rest, this item on the center of gravity, okay, which it looks like I'm off just a little bit. If I can put a support directly beneath the center of gravity, okay, then all of these particles over here are pulling down, okay, and actually exerting a torque. They are wanting to spin this meter stick this way, and all of these over here are being pulled down by gravity. They're exerting a torque and wanting to pull it this way, but if I'm able to put my support right below the center of gravity, then they will completely cancel each other out, okay, clockwise and counterclockwise, and it'll be totally balanced. Does that make sense? So there's, like I said, there's some interesting things about center of gravity. We're just going to just briefly talk about it. Gymnasts, kinesiologists, and things like that. There's all sorts of interesting calculations that you can do with, where the human body is and where the center of gravity is, and it's going to be at different places. They actually have, in your book, there's a diagram. Do I have it here? I don't know if I have that image. Maybe not. They've actually found, okay, for the feet, center of gravity is about right here. Your thighs, your calves, your torso, your arms. If you look in your book on page, there it is, page 205, they've got a great diagram of where they've approximated the center of gravity is on a human, and then you can do all sorts of calculations and figure out new moves and different things like that. So this gymnast, we can actually say, all right, we're going to treat it as if we're going to objectify her. Sorry, this is just that's just the physics of the matter. We can actually treat her as if all of her all of her mass is centered right there, and that's the symbol that we use. This little black and white sort of checkerboard thing. Anyway, so the total gravitational torque can be calculated by assuming that the net force of gravity acts on a single point. So we don't have to do a million calculations. All right, well, how much torque is being caused by these molecules being pulled down, and by these, and by those, and by all the way down the line? We just say, apply her whole mass, gravitational force right there. All right, so the very first problem that we have, you can hit the lights now, Gabrielle. Something kind of like this meter stick, but instead it's a flagpole. All right, it says a 3.2 kilogram flagpole extends from a wall at an angle of 0.25 newtons from the horizontal. Its center of gravity is 1.6 meters from the point where the pole is attached to the wall. What is the gravitational torque on the flagpole about the point of attachment? And so I'm going to pass out a couple of these meter sticks. Go ahead and hold this meter stick, or if you want to, just hold a pencil out there, okay? Hold it at about an angle, so you will actually feel, hold it at the very end, you'll feel gravity is wanting to pull it down. If you're going to hold it in place, you have to give a little bit of you have to put a little bit of rotational force there. See what I'm saying? So pass the meter stick around here. So try to just hold it at that angle, and you'll feel what I'm talking about. The weight is actually, its gravity is exerting a torque on it. In that case, Shelby is exerting a torque on it as well. Alright, share and share like. Pass the meter sticks around there. So hold it there, hold it at the very end.
Oh, there, you gotta make sure.
So, Kimmy, do you feel it? You feel how it's just like, I mean, you've got to exert a torque to hold that up. Now with the pen, it's really not. Hey, share and share alike. Give it to that table back there.
Oh, I didn't know they didn't have.
Kim, do you feel it? Hold it at the very end. Hold it at the very end, and hold up at an angle. All right. Do you feel gravity wanting to rotate it? Okay. That's what's going on right here at this hinge. This flagpole is really putting a lot of torque. And they say, what's causing it? Well, technically, what it is gravity is pulling this particle down, this particle down, this particle down. It's pulling all of those particles down, okay? But fortunately for us, we don't need to find the torque caused by gravity exerting a force at a distance. We don't need to calculate all those different torques. We're just going to say, hey, you know what? We're going to pretend like all of the mass, all of those molecules are right here, okay? And it's a mass of 3.2 kilograms. So all of the gravitational rotation causing on this, the torque, is focused right there. So we have at a distance of 1.6, and we're going to be able to do some calculations here, okay? We have theta of 25 degrees. They want us to find torque. Now, I'll leave the meter sticks around, just don't knock off my camera there. Does anybody remember the formula for torque? We're going to figure out how much is this wanting to twist that. R, keep going. F sine theta. What's theta? Yeah. Would it be 25? Well, that says theta, and this says theta, but we're not guaranteed it. Technically, theta is the angle between the force and what we call the radial arm, right there. So is it always going to be what?
No, like, you're supposed to subtract, but...
Hold on. Ask your question, Gabrielle.
No, I'm fine, I got it.
Okay. Does your formula chart have theta mentioned on your formula chart for, is it RF sine theta? What is it? It really doesn't matter, but just go ahead and tell me, what does your formula chart say? If you don't have your formula chart, don't just sit there, get your formula chart. I'll see you tell.
It says F sine theta.
Is it?
Yeah, RF sine theta.
Do you find it yet? Right there. R perpendicular or RF sine theta. Okay? Now, this is where you have to be smarter than the average student. Okay? You can't just be like, oh, it's theta, and oh, there's theta, I must just plug in 25. Okay? It's not. No, it's not that at all. No, what I'm saying is, this formula, you have to understand what those different terms mean. This means the radius, the distance from the hinge point to where the force is acting. No problem. That actually happens to match what this diagram labeled as R. Okay? You have to know what F is. F is the force. Well, there's no F shown here. Well, you're already smart physics students. What force is exerting here at this point? Weight. The force is weight. So you know, based on your physics knowledge, that F really, in this case, is the W, okay? So no problem. Now, similarly, as a physics student, you know that this theta right here refers to the acute angle between the force and the radial arm, okay? So this angle right here is what this theta is referring to, okay? The diagram is showing that they're calling this angle over here, they're giving it a name, they're calling it theta since that's a standard name, but that's not the number that you're going to plug in here. You're going to plug in Well, let's see, this is a right angle. 90 minus 25 is
90 minus?
65. Okay, fine. 25 plus 90, subtract that from 180. Okay, whatever. All right, you're gonna plug in 65 degrees. Now you're like, oh, are they really just trying to confuse us? Well, possibly. All right, but this is also designed to make it so that you have to understand what this formula is, and you're not just plugging stuff in. Okay, if physics was as easy as just plugging stuff in, then I mean I could teach a 7th grader how to do physics. But this is AP physics. Okay. Why would they give you this angle instead of this one? Well, this is kind of a real world situation because you're not going to be able to measure where this 65-degree angle. You're not going to be able to find. Oh, I'm going to find the center of gravity, and then I'm going to measure that from the vertical distance down. No, you're going to take a protractor out there, and you're just going to measure this. Or you'll take your iPhone and you'll just sit it on here, and you'll put it on the compass setting or whatever, and it'll be able to tell you what that angle is. Okay. And so that'll tell you what the 25 is, but then you have to be smart enough to realize, okay, the 25 is not what I'm plugging in. I'm plugging in 90 minus 25, which is the 65. What's the weight force? 3.2 times 9.8, the mass times the gravity. Okay, that's enough talk. Let's just plug in the numbers. So we've got 1.6 meters times the force, which is the mass times gravity, so 3.2 kilograms times 9.8 meters per second squared times the sine. Not everybody has a calculator. If you have, grab a calculator if you need one, so you can do it.
It's 50.
Okay, some people don't have one. There you go, you have one. We'll pass it back to you. Yeah. We've got enough people check that.
Wow.
Sine of 65 degrees. That's going to be a meter, kilogram, meters per second squared. That's a newton. So our answer is going to be in Newton meters. Anybody have an answer for us? 45.
45%.
Let's round it to 2. They only gave us 2, so we're going to give them 2. Okay? Final answer, do we agree with that? Seem logical? So one problem with it.
Oh, because it's going down.
Torque is a directional concept, okay? You can have positive torque or negative torque, okay? So the answer here is the torque is negative. How are you going to decide that? Well, just the way you know that. That way, if it's going this way, it's negative, and if it's going like that way, then it's positive, clockwise and counterclockwise. Okay? All right. That's pretty much how you would solve these type of problems where you've got the center of gravity and you've got your torque equation. We're going to move to something, we're not going to mess with that. The torque due to gravity when the pivot is at the center of gravity is 0. We're going to do something which is going to help us out tomorrow, but also a little bit today. We are actually going to calculate where the center of gravity is on, let's say you have this this dumbbell, okay, or barbell, whatever. See, it's got, let's say you have a rod, okay, and you have a mass over here, and you have a mass over here on this end. We want to figure out where that center of gravity is, okay? You're like, well, this one's obviously more than this, all right? This is a very, very simple problem, but I'm going to show you why this is helpful. Give me that meter there, Celine, will you? Thank you. Okay. All right. We've already discussed, now this is actually a pretty nice object because it's uniform and the density is pretty consistent. So if you were to guess where the center of gravity is, where would you say the center of gravity is? It's in the middle, okay? That's fine. But what if I wanted to find the center of gravity of something that maybe wasn't uniform for whatever reason? like a stapler, okay? Like I wanted to find where the center of gravity is here. All right? I might have to do a little bit of trial and error, right? Okay? If you're in the process of, if you're building something or you're designing a part, or something's going to be moving or whatever, you need to know where the center of gravity is for a whole bunch of different reasons. Sometimes if you've got it spinning, you want to spin it. If you want to support it, you want to support it on the center of gravity. A lot of things are very complicated. You know, they've got some sort of weird shape. Who knows? You know, it could look. I don't want to draw a stapler, but anyway, a lot of things just generically might have a whole lot of mass over here, but maybe they've got some, you know, maybe it's kind of less dense here, and then maybe a whole bunch of mass up here and stuff like that. And so the problem is that it's not uniform. It's not the same thing all the way across, so you just find it in the middle. Okay? What you can do is you can identify, you can break this down into parts. You can say, okay, well, this thing is a lot of the mass is centered around there. There's a lot of mass that is centered around there, and there's a lot of mass which is centered around here. Okay? So I'm going to turn this complicated structure into maybe 3 regions where the weight is centered, okay? The human body is kind of like that. If you saw that picture, they took the human body, they said they took the forearms, they took the arms, they took the trunk, the torso, and the head, and you can find the center of gravity of some of those different places, and then you can kind of combine that to do some interesting things. If you break that down into the most basic situation, what it turns out to be is just any object, whatever it is, you can think of it as a bar with some mass over here and some mass over here. Okay? Now you say that doesn't, well, it's not necessarily equal, then it's very obvious it's right in the middle. But if it's unequal, then you have this situation. And what we're going to do is we're going to find out a formula for the center of gravity, okay? And then, if you want to make something a little bit more complicated, well, then you just add another mass on there. And then you say, well, there's also a really heavy mass right close to the center, and then you put that on there. Then there's a little bit of mass over here as well, and you can start making a more and more complicated model of something by just adding on different masses. And then you can also start taking it vertically. So you can say, actually, this whole thing looks like this, and there's also a little bit of mass over here, so you have you bring the y dimension into it as well. So the thing is that anything, no matter what, even if it's a complicated spacecraft like the Dragon capsule up there, okay, you can reduce it down to something very simple, just as, well, there's part of it over here, and there's part of it that's over here, and they're unequal in mass. So what we're going to do is we're going to find out where is that center of gravity. Where is the point that if I put a pivot right there, this strange barbell would be completely balanced, okay? So that's probably a longer explanation than this is actually going to take, so I'm sorry. So here we go. If this is completely balanced, then the torque caused by this and the torque caused by this object over here will completely balance out. Does that make sense? Hopefully it does. So since it's completely balanced out, we could say that the torque counterclockwise plus the torque clockwise equals 0. All right, that's kind of the big picture where they're both completely canceling out each other out. First, we're going to find the torque caused by mass 1. So we'll call that torque 1. And if you remember, the formula is F, R, RF, doesn't matter the order, sine theta, where theta is the angle between the force and the radial arm. Now, since this is weight and it's being pulled straight down, what is that angle between the weight and the arm? 90 degrees. Okay? Does anybody know what the sine of 90 degrees is? 1. And we get the same thing over here. So it turns out that if you've got something pulling at 90-degree angles, it's awesome. It's just the force times the distance. okay? And the weight is equal to the mass times gravity. So we can say mass 1 times gravity. So torque 1 is weight times R times the sine of 90 degrees. So that's just going to be weight is mass 1 specifically, times gravity, times the sine of 90, which as we said is 1. Oh, times the radius. And that radius is the distance from the center of gravity to this point, which is R1. And if we want to be a little bit more specific, we'll slap a number line on this. They've got a number line over here. Someplace over here, that's position 0. That's the origin. X1 is going to be where this item is located, and XCG is the location of the center of gravity where we could put the pivot to make everything fully balanced. So this distance right here is going to be the difference between XCG and X1. That's R1. So we could write torque 1 is mass 1 times gravity times XCG minus X1. And we can have the same situation now over here. Notice 90-degree angle, weight 2, which is mass 2 times gravity. So torque 2 is the weight of object 2 times the radius of object 2 times the sine of 90 degrees. So torque 2 is mass 2 times G times R2, and the sine of 90 is 1. So torque 2 is mass 2 G, and then R2 right here is the distance between X2 and XCG. So we can say X2 minus XCG. Gabrielle, if you don't mind, go and hit those lights. So what we set up here was that the net torque, which is the clockwise, or I should say counterclockwise plus clockwise, is equal to 0. So everything which is going counterclockwise is this. So that's that torque. So we have M1 G, and you can carry this on over to that white space on your notes. XCG minus X1, and then plus. Now I made one mistake over here on torque 2. Notice what direction this is moving. Clockwise, yeah. So this is, I should have put a negative right there. So plus a negative M2 G X2 minus XCG. So adding a negative, basically subtracting. I can add this to both sides, and I have mass 1 times gravity times XCG minus X1 equals, bring this over to the other side, M2 G X2 minus XCG. Now hold on a second, what in the world are we trying to figure out from this? Anybody remember? XCG.
Yeah.
I'm trying to find the position where to put this pivot. Where along this bar should I put it? So I'm trying to find XCG. We'll need to do a little bit of distribution and then try to get XCG all by itself. So a little bit of algebra here, but not very much at all actually. M1G XCG minus M1G x1 equals m2g x2 minus m2g x cg. I want to get all my xcg terms over on the left-hand side. So this one and this one. So this item right here, I'll just leave as is. M1g xcg. I'm going to add this to both sides, so I have plus M2g xcg equals, this one stays as is, M2g x2, and I'm going to add this to both sides to bring it over here, plus M1g x1, almost finished. Notice I have an xcg in both of those terms. So I can factor out an xcg. What's left over here is m1g plus m2g. Over here I have m2g x2 plus m1g x1. In fact, there's something that every single one of those terms has. We should have taken care of this. Hey, G. Thank you. That's right. They all have a G. All right, a G, a G, a G, a G. So I can divide this by G, and I can divide that by G, and all the G's go away. All right. So divide that. I divide everything by G, and they're all gone. At the same time, I'm going to divide this side by M1 plus M2, and divide this side by M1 plus M2, and finally get a good answer here, that the position of the center of gravity, xcg, is equal to, I'm going to just rearrange this, rather than having M2 x2, M1 x1, I'm going to put the ones first. M1 x1 plus M2 x2 divided by M1 plus M2. And that looks really complicated, but in actual fact it's not. It's really quite elegant. The position of the center of gravity is, you take the mass of object 1 times its position, plus the mass of object 2 times its position. It's not random, it's M1 x1, M2 x2, divided by the sum of their masses. Okay? If we want to have another object on here, if we want to add a third object to sort of get another approximation, mass 3 at position x3. The really nice thing is this formula just carries on. It just would become plus mass 3 times its position x3 over, you just would add on there mass 3. If you want to make this a little bit more complicated by adding on another fourth one, you can continue that process on and on. It's just going to be the product of the mass times its distance divided by the total mass of the object. Okay? Now, you say, that's great. That's for dumbbells, or barbells, or whatever. How many times do we have to, we're never going to really probably need in any sort of engineering or gymnastics context or anything like that, we're never going to deal with something that simple. And the answer is you're right. But you always start with something simple and then make it more and more complicated. If, let's say, we had an object which not only had length, but also had width or height here, okay? And we had positions up here and an object up here, an object up here. Well, now you just would extend a y-axis, okay? And it would have y values, y1, y2, so on and so forth. And all of that same mathematics is exactly identical with the rotational aspect. And the y position of the center of gravity is equal to the mass at its y1 coordinate plus that mass 2 at its y coordinate plus so on and so forth, divided by mass 1 plus mass 2 plus mass 3, which ends up actually equaling the mass of the object. So let's say if you had something that was just completely flat like a piece of paper, but you could find out where its center of gravity. And then now you're thinking, okay, well, how many times are we going to deal with something that's completely flat? You're normally going to have something that's going to have, length, width, and depth. And guess what? Same exact process for adding a z variable, okay? It would just be the z coordinate of the center of gravity is mass times its z coordinate plus the y, plus mass times its next z coordinate, okay? And that is how we are able to find the center of gravity of complicated shapes and complicated structures, okay? In fact, what you can end up doing is with more complicated things, you can add up all of the different particles, okay, using something called the limit process, which you'll learn in calculus. And you can actually add up all of the infinite particles that are here, and you can figure out exactly where it is. You can add up an infinite number of things. And calculus allows you to do that, okay? So, this sort of stuff is used if you're in industry, if you're building something, if you're manufacturing something. Have y'all ever seen a lathe? All right, there's wood lathes and there's metal lathes where you've got something where it's spinning around, okay? And it's and then it's kind of spinning around like this, and then you can take a tool and you can kind of get it at an edge. You got where's our art people at? Your clay structures, right? Okay. What's part of the thing that Have you ever messed with pottery? Have you done throwing and wheels and stuff like that?
I'm not in.
Not yet. Not in that class.
We have a class for that. But.
Okay. Wood lathe. If it gets off center, if it's rotational center of gravity, it's gonna fly off. If you put clay on there, it's gonna want to wobble and it'll actually fly off because it'll slowly start spinning, farther and farther off of the center. Unless you get it dead center on, you're able to mold that clay so that its center of gravity is above the very middle part of the wheel, which is spinning. Otherwise, you're going to have more mass on this side, which is going to start to throw it over that way. So you really got to kind of manhandle it or woman handle it, okay, when you first throw it on there, okay? Anyway, so all of this sort of stuff comes into play. We're just going to, based on this equation, this is one of these situations where the derivation of the equation is really like a mouthful, but applying it is really, really easy, okay? So let's do a very quick example. Let's say you have an object which we're going to model it, we're going to simplify, we're going to dumb it down into just a 10 kilogram part of it over here and a 5 kilogram part of it over here, and we want to figure out where the center of gravity is. Is it going to be right in the middle? Why not?
Because the different masses.
Different masses. You got it's heavier on this end. Okay. They might say, oh well, it's not really. Well, maybe the object looks, something kind of like this, and more of the mass is over here. And in fact, it may even extend over there. But we're going to treat this whole end as if the mass is located right there. We're going to treat this whole end as the mass is located right there. And boom, finding the center of gravity is literally this easy. All right. Plug it into the formula. Mass 1. 10 kilograms times distance 1, or location 1, sorry, 0, plus mass 2, 5 kilograms, its location, 1, divided by the masses added up, 10 plus 5, 10 plus 5. So it turns out to be 5 over 15,
1/3.
which is 1/3, or we'll say just round it down, 0.3 meters. So if that's at 0 meters, this is at 1 meter, this right here is at 0.3 meters. Is that what you would expect technically it's 0.3 feet. Is that what you would expect where the balance, where the center of gravity would be?
About. Yeah, well,
Yeah, because it's heavy.
Isn't that close to-
yeah.
That's not only because it's heavier, okay, but look at it, it is exactly twice as heavy, right? And you've got exactly twice the distance over here. This is 2/3, this is 1/3. Y'all see that? So in order for something to be balanced, if it's twice as heavy over here, you'd want that pivot closer. Otherwise, as we found out, if you're farther out, then there's more torque. Okay, so this is how you would have the torque from the 10 kilograms completely balanced with the torque from the 5 kilograms. Now, to wrap up what we talked about center of gravity, okay? What it is, and where it's as if where you consider all the gravitational torque is exerted on that one point, okay? And we've got a basic formula here for finding it in the x direction, but you can extend that to the y and the z direction, okay? Tomorrow we'll talk about something called moment of inertia. How fast something's spinning and what changes that.